Hello everyone, I am Jim and today I'm going to present my work, which is multi-car convex feasible set algorithm in trajectory planning. This is the outline of this presentation. Let's first take a look at the motivation. Nowadays, autonomous vehicle is in fast development and it's highly likely to be the future. So high-performance trajectory planning module is a requirement in autonomous vehicle. However, the current prediction and plan structure of the planner may cause instability or deadlock between multiple vehicles. So we start to think if there can be a consensus planner that can plan trajectories for multiple autonomous vehicles together, then it can solve the issues. Based on this, we extended the basic convex feasible set algorithm to plan trajectories for multiple cars. So, based on the original convex feasible set algorithm, the contributions are as below. First, extended CFS to solve multiple vehicle planning problems. Second, proposed a novel convexification method to obtain correct-oriented maximal convex feasible set in high-dimension space. And then several typical driving scenarios are simulated to prove the feasibility of the algorithm. Now let's take a look at the CFS algorithm. CFS algorithm is an optimization-based planning algorithm. It extracts convex feasible set out from non-convex feasible set during optimization and solves the optimization problem for iterations until final convergence. It allows more functionalities other than collision-free in the trajectory by adding various composition to the cost function. The pseudocode of the algorithm is as below. First, we initialize the trajectory. Then we go into the while loop, and inside the while loop, we will do convexification and optimization. If the optimization criterion is satisfied, then we break out of the loop and return the trajectory result. If not, then the current trajectory result will be used as the reference trajectory, and we will go into next optimization iteration. After knowing the basics of the CFS algorithm, let's get into the multi-car CFS algorithm. The first step is also initialization. Denote n as the number of cars, h as the number of trajectory points, xij to be the 2×1 vector of xy coordinate of the ith car at j's trajectory point. So the initial reference trajectory can be written as x11, x21, all the way to xnh. In the figure at the right side, there are two cars, and each car has a trajectory containing two waypoints. So in this case, the trajectory variable x would be 0, 0.75, which is the first point of car 1, 0, 0, the first point of car 2, 1, 0, the second point of car 1, and 1, 1, the second point of car 2. The cost function of the algorithm would include three parts. The first one is cost of trajectory differences, which makes sure the planned trajectory maintains the tendency of the original trajectory. The cost of trajectory velocity penalizes the accumulative velocity magnitude along the trajectory. The cost of acceleration is the most important one, which penalizes the accumulative acceleration. This can make the trajectory more smooth and comfortable. Every cost is quadratic cost with regard to trajectory x. After defining the cost function, we need to define the constraints. The algorithm considers two constraints. The first one is distance constraint, which basically constrains the distance between two cars to be larger than the safety margin. The second one is the priority constraint. It allows cars with higher priority to pass first when two cars will arrive at the same location at the same time. Let's first take a look at the distance constraints. The square of distance between two cars' position, x1 and x2, are the dx1, x2. Denote c as the square of safe distance, then the constraint function would be dx1, x2 minus c. And the non-convex feasible set would be tau equals phi x1, x2 to be greater than 0. Doing Taylor expansion on x1 ref, x2 ref, keep the first order term the convex feasible set is obtained as F. It is a linear feasible set, and the challenge becomes how to choose the reference points to obtain maximal convex feasible set. So why does reference points matter? The picture shows the situation for a 1D constraint function gx larger than 0. If we use x1 as the reference point, then the linear feasible area would be the red dot line. And if we choose x2, then the linear feasible area would be the blue solid line. It is clear that the reference points x2 will give us larger convex feasible area. The traditional CFS algorithm chooses reference points as the cars location computed in the last iteration to ensure the feasible set is near cars location and has proper orientation. However, in multi-car scenario, this traditional way might not be able to provide maximal feasible set. The convex feasible set in our case is this. If we denote vector E to be the unit vector along the direction of x1 ref minus x2 ref, lambda be the distance between these two reference points, and if we divide lambda on both sides of this inequation, then we got the formula as below. It is clear that if lambda equals square root of c, then the right-hand side will be minimum, and the feasible set becomes maximum. This also means the constraint function phi x1 ref x2 ref to be 0. But it is not enough to just obtain max feasible set. Let's look at this one car example. The car has to maintain safe distance with point O. If we choose C as the reference, then we will get feasible set A. If we choose D, then we will get feasible set B. Obviously, feasible set A is more proper for the car point to locate at. So in the two-car scenario, we choose the reference points as x1r, x2r, and x1r minus x2r equals square root of c times e. Here e is the unit vector between trajectory points from last iteration. By this, we can get the correct oriented maximal convex feasible set. Now let's take a look at the priority constraint. In this figure, car 1's trajectory is k1x plus b1 equals 0. Car 2's trajectory is k2x plus b2 equals 0. So if car 2 has a higher priority, then this means car 1 has to wait on one side of car 2 until it passes. So the constraint design is k1 x21 plus b1 larger than 0, k1 x22 plus b1 smaller than 0. This means the 2 points of car 2 should remain on one side of car 1's trajectory. Meanwhile, the car 1's 2 points should remain on the one side of car 2's trajectory. Okay, now let's look at some simulation results. The first simulation result is an intersection scenario. Here, the original trajectories of car 1 and car 2 will collide with each other at the intersection point, but the planned trajectory ensures the car with higher priority, in this case car 2, to pass first. Meanwhile, they maintain a safe distance at each time step. This is the overtake scenario, where the car 2 wants to pass car 1 that has low speed and avoid car 3 which is driving toward it. The planner managed to do this. If we check the speed profile of car 2 and car 3, we find that the planner plans the car 2 to accelerate and car 3 to decelerate in the beginning, so that they will still maintain safe distance when car 2 is overtaking car 1. The third scenario is a crowded 9-car scenario where there are some cars simply moving forward and some cars doing lane change. The trajectories are all smooth. One interesting phenomenon is, in the circled area, the car 9 is veering right a little bit. This is because car 2 in front of it is doing a lane change, and the car 9 wants to maintain a safety distance with it. The running time complexity is On squared with regard to number of cars and On with regard to number of trajectory points. This is because number of constraints is increasing with the number of cars and waypoints in the same magnitude. These are some conclusions and future work about the multi-car CFS algorithm. Thank you very much for your attention. If you have questions, feel free to reach us.